I'm going to talk about network meta-analysis. And to start with, network meta-analysis has been extensively used in healthcare decision-making to assess the relative efficacy or the relative safety of multiple interventions within a single framework, so within a single analysis. So for interventions, the methodology is well established and has been very well framed throughout the years. But when it comes to diagnostic accuracy, as we discussed earlier, there is a less established precedent for its extension to capture these test accuracy comparisons. So therefore, to capture these advancements in these fields, we conducted a scoping review. So we searched PubMed, Web of Science, and Scopus databases up until the 3rd of March 2021. And our aim was to identify both methodological and application papers that reported a model that was developed specifically for network meta-analysis of diagnostic tests, that is DTA-NMA, or they use the hierarchical meta-regression method to compare at least 3 index tests, and I'm going to explain this further in the next few slides. So our search yielded 50 publications in total, 10 of which were methodological and 40 application papers. So we can observe the distribution of eligible publications that were finally included beginning in 2010, with the first methodological paper appearing in 2014. So across these 10 method publications, there were 11 models described, plus the 2 hierarchical models using the meta-regression approach. So the properties of these models differ, and these differences may impact the interpretation and consequently decision-making. So all of the models, the DTA-NMA models, are based on the simultaneous analysis of multiple DTA studies and they account for most of them account for between study correlations between sensitivity and specificity that is caused by the threshold effects, as you saw earlier. So the most commonly used model is the bivariate or the HS-ROC meta-regression approach, where a covariate for the test type is included. And this is used to explore whether sensitivity and specificity differ between the tests. So all of the DTA-NMA specific models are compatible with multiple index tests, as expected, although 2 of them need extensions to do so. So this means that in the original paper, the model was developed for 2 tests, but the extension is feasible. Then all but 1 model were developed in a Bayesian setting, and only 3 can handle imperfect reference standards. So in terms of multiple thresholds, all but 1, that is the model developed by Owen et al., only this model can handle multiple thresholds per se, which means that it doesn't account only for the threshold effects, but through this model, we can obtain different estimates at the various thresholds included. And finally, in terms of data required, one method was a contrast-based approach, which allowed for modeling only paired and multiple test studies, which means that single test studies, as you saw earlier in the network plots, cannot be modeled using this, cannot be incorporated in this model. So this should be excluded, and such an option may lead to a reduced and less informed evidence network. And then the majority of the methods require the joint classification tables of the tests per study and account for the correlations between tests. So what are these joint classification tables? Such tables summarize and compare results of multiple index tests against a reference standard and across tests. So in this example, where we explore the target condition is COVID-19, and we have 2 index tests, rapid antigen test A and test B. Then we would need to display the outcomes, that is the positive or negative test results, for both antigen tests against the reference standard, which is shown on the left, while on the right, we have another table which displays the results of index test A against index test B. So If such tables or the relevant information is not provided in a DTA study, then this can be constructed when the individual participant data is available, which, as we are going to see, is not often it's not often encountered in such publications. So in terms of application papers, out of the 40 such papers that were eligible for inclusion in our review, the majority, 29, employed the bivariate or HS-ROC meta-regression approaches. And then a smaller number, only 5 of them, incorrectly used the NMA model for interventions. And for 3 publications, the methodology that was followed was unclear. And finally, we need to note here that there were 3 models that applied a DTA-NMA model, and this included the Medden-Saffer model and the Nyaga-Nova model, which we are going to see later. And it is important to note that most of them were included, the majority of them, 33 out of the 40, were published in general medical journals, including the Cochrane database of systematic reviews. So we then searched for the raw data of these publications, and the 2x2 tables of the tests against the corresponding reference standard was available for 32 of the networks. And out of the 32, on 8 networks, we had available data at multiple thresholds per study. So we aim to assess the performance of the models using the data available. So we considered only the DTA-NMA models that required the 2x2 tables. And we also considered the bivariate meta-regression models was used as the control, let's say, model. So based on our collection of 32 data sets that were described previously, we applied these 4 models plus the bivariate meta-regression. We used the code provided in the relevant publications, and we applied the models using R-star and Winbacks, while for the bivariate meta-regression model that was applied through the LME4R package. So some more details on these 4 models, plus the bivariate meta-regression approach, which was the control, and I'm going to start with that one. So in the bivariate meta-regression model, as I said earlier, a covariate for the test type is used to explore sensitivity and specificity between tests. So in this model, we assume that the participants who are given different tests are independent subgroups within each study. So we don't account in this way for the within study correlations between tests. So if a study, a DTA study, is exploring 2 index tests, and these are given, for example, to the same participants, there is some correlations since these are the same observations. So under this model, this correlation is ignored. Then regarding the ANOVA model, this DTA-NMA model is based on repeated measures design. So its individual is considered to have been measured across the different tests within its study, and therefore can be treated as a repeated measurements. So this is actually a 2-stage hierarchical model inspired from a 2-way ANOVA model, and we capture the within study correlations between tests, and we allow for variation in the that is heterogeneity in the true study specific sensitivities and specificities. And we can consider also within study between tests variability, heterogeneity, and between study variability as well. In terms of the beta binomial model, this DTA-NMA model is also a 2-stage model. It is based on a bivariate beta distribution, and the authors used a copula density to capture the dependency between sensitivity and specificity. And similarly to the ANOVA model, there is a variation allowed in the true study specific sensitivities and specificities. Okay, and then regarding the hierarchical latent class model that was suggested by Medden and Saffer, This is the only contrast-based model. So this is based on the differences between the different tests in the network. This model allows for perfect reference standards. And as we said earlier, it's due to its contrast-based nature, let's say, its single test studies cannot be accommodated in this model. And also correlations between tests from the same study are ignored. And finally, the variance component model. So this is an extension of the ANOVA model. And in this extension, it has been made feasible to incorporate different tests, but also including multiple thresholds per study. So this model actually treats different test thresholds combinations as separate tests and provides results on this combination. So for example, if we had a study exploring a single test, let's say test A, at two different thresholds, threshold 1 and threshold 2, then this combination, test A threshold 1 and test A threshold 2, would be considered as two different tests, and sensitivity, summary estimates for sensitivity and specificity would be provided. So we assumed common within network between study heterogeneity within its model, and we estimated two between study variances, one for logit transformed sensitivity and one for the logit transform specificity. So I have to give some explanations here. So the between study heterogeneity refers to the variability in test performance, in test accuracy between studies due to variation in the study-specific effects, while between test heterogeneity refers to the variation within studies due to, let's say, due to repeated sampling. Okay. So these box plots describe our results. These correspond to the box plots of sensitivities and specificities and standard errors of the logit sensitivity and specificity, as these were estimated in the meta-regression, the DTA-NMA models. So the orange corresponds to sensitivity and the blue corresponds to specificity. So what we can observe from our results is that the sensitivity estimates obtained from the median suffer, that is the third column, were on average in agreements with the meta-regression models, but specificities tended to be smaller. Also, the Nyaga-Nova model had good agreements with the sensitivity obtained from meta-regression models, but again, it's the meta-regression model estimated higher specificity estimates. And on average, we observed a good agreement between the Nyaga beta binomial model and meta-regression on sensitivity. But again, the problem consistently is that meta-regression consistently estimated higher specificities. Then Nyaga beta binomial model was associated with the lower between study heterogeneity for both estimates of sensitivity and specificity. And we consider that this might be indicative of better fitting of the model. And finally, regarding the Owen model, which is not displayed here, so applying this model showed that different test thresholds included may cause differences in the results, as the different combinations of tests and thresholds are considered as separate tests finally in the model. So to summarize, the meta-regression models have been widely used over the years, but there is a main limitation. This model ignores such models, both Data-Shock and the bivariate approaches for meta-regression, ignore the within-study correlation between the tests. So we assume that in this case, we assume that observations between tests assessed within the same participants are independent, which does not hold. This assumption does not hold, and it's unlikely to hold, because meta-analyses are dominated by studies with within participant designs. So all participants receive all the tests usually. And when we adopt this model, we might end with incorrect estimates of standard errors and also incorrect estimates of summary sensitivity and specificity, and also errors in between study variances. However, this meta-regression approach is conservative and is currently accessible to many reviewers. So there are more advanced methods and models that have been developed over the last years, and most of these account for the correlations between multiple pairs of sensitivity and specificity across tests and within a study. So what is important to keep is that the NMA methodology that has been developed for intervention studies is not applicable to DTA studies. And there are three main reasons which have already been discussed. So the first is that tests are given to the same participants. So we have correlated observations, which using the methodology for interventions, these correlations are ignored. Secondly, there are two effect sizes, correlated effect sizes, that we should consider at the same time, and these are sensitivity and specificity. And lastly, the network geometry is different. So in terms of interventions, we cannot consider yet in network meta-analysis single arm studies, but in network meta-analysis in networks of diagnostic tests, single test studies are included, since the reference does not act as a node within the network, but only as a bridge. So up to date, there are 11 models that have been developed specifically for DTA-NMA, plus the two hierarchical methods. And I'm aware that I've seen recently that there is also another model extending the Niaga-NOVA model to capture different thresholds. I've seen this, I think this was published not published yet, I've seen that's in a poster by Dr. Derezea, but we're looking forward to the publication. So despite that DTA-NMA models are an important contribution to the fields of diagnostic tests, there are still several limitations that may compromise their wide implementation. So the difficulties have to do with software and model complexity. So as you would have seen, most of the models use Bayesian setting, and this can pose programming barriers. So code availability is limited, rarely reported in publications, and a main issue is that it is not yet implemented in popular statistical software or user-friendly programs such as an R package, for example. And there might be also convergence issues. So this often arises in multivariate approaches, and especially as the number of tests in the network increases. This happens because the number of parameters that we need to estimate within the model increases as the number of tests in the network increases. For example, in the datasets with COVID-19 tests that we're going to see in the next slides, this network required more than 48 hours to run the Niaga-NOVA model. And in general, the whole process can be time intensive. So there are also data challenges. We might encounter missing participant data, that is, within the same study, not all participants receive all index tests of interest. So there is a missing pattern that needs to be captured within the models. And then, as we saw before, to apply the models that require, we have applied only the models that require the 2x2 tables. To apply the models that require the joint classification tables, we need such data, which is not, we discussed earlier, are not often reported in DTA studies and would require the individual participant data to derive the relevant information. So these data availability issues pose even more difficulties. So there is not a single valid method for DTA-NMA analysis to choose. There are, well, on average, the different methods that we saw gave similar results in terms of sensitivity, but the bivariate meta-regression approach provided higher estimates of specificity. So the selection among the DTA-NMA methods should depend on the data to be analyzed, such as the inclusion of different test thresholds, reference standards, and study designs, as well as software familiarity. The meta-regression model ignores the within study correlation between tests, so not the best approach, but we need to keep in mind that even within the rest of the models, selecting a different model may impact on the NMA results, and especially for specificity. So, and as we discussed before, some of the models require the joint classification tables, and this poses difficulties in their availability and data sharing. So this might be, again, a barrier to applying this. And now I'm going to go through an example of a diagnostic test accuracy network meta-analysis. So more than a year ago, Health Canada and the Public Health Agency of Canada commissioned the team to conduct a review to determine the most sensitive or specific rapid test for the diagnosis of COVID-19. So the team was set up considering to include policymakers who requested evidence, at least one clinician and content expert, two patient partners, content experts, research methodologists, and statisticians. So the research question was set as follows. In terms of populations, adults and children were considered who were screened or suspected for COVID-19. In terms of index tests, the rapid antigen tests or rapid molecular tests for the diagnosis of COVID-19 infections were considered. So the target condition obviously was COVID-19 infection, and the reference standard that was used was PCR tests. So in terms of study design, we included both RCTs and observational studies, which provided the 2x2 table data. So each test against the reference standard. The outcome was sensitivity and specificity of both kinds of tests, and this was registered also in Prosper. So as a next step, we performed data analysis, and we started with a basic descriptive analysis, including some details about the country and the type of contact and the type of the rapid test. And when the eligible studies, firstly, to assess the diagnostic accuracy of each index test, we perform a random effects meta-analysis using the bivariate model. And then, when the eligible studies formed a network of index tests, we performed a DTA-NMA, and we used the totality of the evidence in a single model, accounting for the correlations between tests from the same study. So we applied the Niaga-ANOVA model, and we obtained the summary estimates of sensitivity and specificity for each test along with its uncertainty, that is, we obtained the credible intervals, and also we provided the estimates of between test and between study heterogeneity. So we also aimed to explore heterogeneity, so we visually inspected the forest plots and we investigated predefined potential effect modifiers. So we conducted some subgroup analysis according to that and some meta-regression. And we also aimed to explore, to assess the transitivity assumption in each of the networks. So transitivity assumption relates to the potential and clinical methodological variation of diagnostic accuracy across the different test comparisons of the network. So what we did is to assess whether the distribution of the effect modifiers were on average similar across the different test comparisons. So we reported our findings following the PRISMA DTA and the PRISMA NMA reporting guidelines to ensure transparency and completeness of our reporting. So overall, as you can see in this network, starting from the left side, we included evaluations of 36 different rapid antigen tests. And this network was informed by 68 studies and approximately 105,000 participants. And on the right, we have the network of 23 rapid molecular tests for COVID-19. This network was informed by 27 studies and approximately 11,000 participants. So the these two networks are disconnected, and this is the main difference again from the network meta-analysis from the intervention networks. And you can, if you notice closer, the reference standard, that is PCR, is not part of the network geometry. So and this is because, I'm underlining this again, as Arji explained greatly earlier, that the reference standard defines only the presence or absence of the target condition, and it is considered the bridge to compare the different index tests. So it's not included in the network. So we selected to present our results using both tables and forest plots. So these are the DTA-NMA results of each index test against the reference standard. So in orange, we denote the sensitivity, and in blue, we denote the specificity. Among the rapid antigen tests, the rapid molecular test, experts express test performed best among the rest, and also fulfilled the minimum WHO requirements that were WHO required a sensitivity greater than 80% and a specificity greater than 97%, while the corresponding best test for rapid antigen test was the COVID Vero test. So results across the studies assessing this test varied, which can be attributed to the differences across the clinical and methodological study characteristics, so further exploration might be needed. And we also summarized the results from the bivariate DTA meta-analysis model. And what we can notice is that the results were more conservative with when analyzed within a single analysis, that is using a DTA-NMA model. So, okay, overall, there is still a lot of space to explore and a lot of things to do. We aim to explore which factors impact on the performance of the DTA-NMA methods. Currently, we need to extend the ranking metrics that are available for multiple outcomes to the DTA-NMA methods. There are already some options, but it could be better to have some metrics that capture these dependencies between sensitivities and specificities and provide a relative hierarchy of the index tests included in a network. The DTA-NMA assumptions, regarding these assumptions, there are needed appropriate methods to explore the consistency assumption in terms of diagnostic test networks, accounting for both sensitivity and specificity. And of course, there are new methods that are required to deal with and account for different study designs in such networks meta-analysis. So simulations might also be needed to assess the performance of the DTA-NMA methods and identify which method performs best and under which circumstances. So we would like to acknowledge our all this effort was part of this scoping review that was published in JCE, and we would like to acknowledge our co-authors for their help and contributions. And of course, here are some resources in terms of DTA, and specifically the Cochrane Handbook of Diagnostic for systematic reviews of diagnostic test accuracy. So I would like to thank you very much for your attention, and we're happy to discuss any questions or issues that might have arisen.